Hey everyone, and welcome to this explainer. Okay, be honest with me for a second. Have you ever stared at a chemistry textbook and just felt totally overwhelmed by the millions of chemical reactions happening around us every single day? It can feel like an absolutely impossible amount of information to process, right? Well, what if I told you there was an actual cheat code to understanding almost all of them? Today we're going to unlock that chemistry cheat code by mastering just 5 fundamental reaction patterns. Let's get started. So, here is our precise roadmap for today. First, we'll cover the chemistry cheat code. Second, the father of modern chemistry. Third, the 5 basic reaction patterns. And finally, the 5 reaction lab.
Section 1. The chemistry cheat code. Okay, let's dive into this.
Beneath all the apparent chaos of chemistry, there's actually this stunning, elegant order. Instead of trying to memorize an endless, terrifying encyclopedia of chemical equations, we can categorize the vast majority of those millions of daily reactions into just 5 basic patterns. It's like a giant puzzle. By recognizing these structural patterns, you can actually predict the products of chemical reactions that you have literally never even seen before. This cheat code takes chemistry from this grueling exercise in rote memorization and turns it into an incredibly empowering, simple game of pattern recognition. And trust me, once you see the matrix, you really can't unsee it.
Section 2. The father of modern chemistry.
Now, none of this brilliant pattern recognition would be possible without the man who established the foundational rules of how matter behaves, allowing these 5 patterns to even exist in the first place. I'm talking about Antoine Lavoisier. He was an absolute pioneer back in the 1700s, but his story actually has a very tragic end. He was executed during the chaos of the French Revolution in 1794. The mathematician Joseph-Louis Lagrange famously remarked, "It took only a moment to cut off his head, but a century might not produce another like it." It is a truly sobering reminder of the immense, irreplaceable genius the scientific community lost that day. But wow, did his legacy change the world? Lavoisier's crowning achievement was proving the ultimate, unbreakable rule of chemistry, the law of conservation of mass. Through meticulously sealed glass containers, he proved beyond a doubt that the total mass before a reaction exactly equals the total mass after. Matter is neither created nor destroyed, it simply rearranges itself. And the rules for how it rearranges? Well, those are the patterns we're about to explore right now.
Section 3. 5 basic reaction patterns. And this brilliantly illustrates exactly how those atomic rearrangements actually happen.
So this is your core toolkit. Let's start with pattern number 1, synthesis. Think of this literally like a social interaction where 2 individual elements decide to pair up and become a couple. 2 or more simple substances combine to form a single, more complex product. The general pattern is beautifully simple here. A plus B yields the combined product A-B.
Looking at some real-world examples, when sodium meets chlorine, they pair up to give you everyday table salt. Hydrogen and oxygen combine to make water. And when solid magnesium reacts with oxygen gas, it synthesizes into magnesium oxide. If you've ever seen a burning magnesium ribbon in a science classroom, you know for sure it produces this absolutely blinding, brilliant white light. That stunning flash is just a synthesis reaction enthusiastically saying hello. All right, let's look at the flip side. Pattern number 2 is decomposition. If synthesis is a couple getting together, decomposition is the breakup. It is the exact reverse of synthesis. One complex compound, AB, breaks apart into its simpler components, A plus B. But here's the thing. Chemical compounds usually don't just fall apart on their own. Decomposition usually requires an energy input from the outside, like heat, electricity, or light. For example, you can use an electrical current to split water back into hydrogen and oxygen gas. Or you can apply intense heat. In fact, heating mercury-2 oxide to break it down was actually one of the classic experiments Antoine Lavoisier used to prove the conservation of mass. Moving right along to pattern number 3, single replacement. The general pattern here is A plus BC yields AC plus B. Picture a dance floor where someone just cuts right in. One element comes in and kicks another element out of its compound. But it's not a random process. It's based on a strict reactivity ranking called the activity series. To win the spot in the compound, the incoming element absolutely has to be more reactive than the one it's trying to replace. Let's see how that crucial rule actually plays out. So zinc is higher on the activity series than copper, right? So if you put solid zinc into a copper sulfate solution, zinc easily steals the sulfate and kicks copper to the curb. Iron will do the exact same thing to copper. But consider copper plus zinc sulfate. Because copper is less reactive than zinc, it's simply not strong enough to cut in. The result? Absolutely no reaction occurs. The activity series is the absolute law here.
Okay, let's level up to pattern number 4, double replacement. If single replacement is cutting in on a dance, double replacement is two couples mutually agreeing to switch partners. The positive ions of two different compounds swap places entirely. This general pattern, AB plus CD yields AD plus CB, typically happens in aqueous, meaning water-based solutions.
So the really crucial point is how you know this partner swap actually happened. Usually, it produces a highly visible physical change. It might create a solid precipitate that suddenly falls out of the clear solution, like the silver chloride you see in our first example. Or, as in the second example, an acid and a base neutralize each other to form liquid water. You are always looking for that new state of matter as concrete proof of the double replacement.
And that brings us to our fifth and final pattern, combustion. This is the big one for global energy. Combustion is a rapid exothermic reaction, which just means it releases a ton of heat between a fuel and oxygen gas. When that fuel is a hydrocarbon, the general pattern is incredibly consistent. It always produces carbon dioxide and water. This reaction is our primary energy source for worldwide transportation, heating, and electricity generation, but it is simultaneously the main source of anthropogenic CO2 emissions.
To firmly ground this final pattern in your everyday life, just look at these common hydrocarbon fuels. When you turn on a gas stove to cook dinner, you're burning methane. Firing up the backyard barbecue, that's burning propane. And when you start a traditional internal combustion car engine, you are burning octane, or gasoline. In every single case, the fuel reacts rapidly with oxygen to release useful energy, carbon dioxide, and water vapor.
Section 4. The 5-Reaction Lab.
Now that you officially hold the cheat code to all 5 patterns, let's see how this builds into real-world application. We're going to take these textbook definitions and put them to the test in a physical, visual lab setting. But before we light a single Bunsen burner, we have a few absolutely crucial safety protocols. Step 1, goggles and aprons are a must. Step 2, and this is a huge one, we cannot look directly at the burning magnesium in Station 1. That intense white light can cause serious eye damage. Step 3, we need to handle the hydrochloric acid with extreme care. And step 4, watch out for silver nitrate. Seriously, if you spill a drop on your skin or clothes, it leaves this stubborn dark stain that takes days to wear off.
All right, so let's look at our lab observation table. When you walk through these 5 stations, I want you to actively connect the thrilling visual evidence you're seeing to the specific patterns you just mastered. At Station 2, when you see that rapid foaming from the hydrogen peroxide, recognize instantly that it's a decomposition reaction releasing oxygen gas. At Station 3, when the solid zinc hits the acid and vigorously bubbles, well, that's hydrogen gas escaping from a single replacement. And at Station 4, when you mix 2 completely clear liquids and an immediate white cloudy solid forms, that is the unmistakable precipitate of a double replacement happening right before your eyes.
We have covered a massive amount of incredible ground today, but I want to leave you with 2 final puzzles to really test out your brand new cheat code. In Station 5, you place a glass jar over a burning candle. Why exactly does the flame eventually go out? Think carefully about what a combustion reaction actually requires. And finally, based on what we learned about the activity series, will solid copper be able to replace zinc from a zinc sulfate solution? Why or why not? I challenge you to apply your new pattern recognition skills to solve these. Thanks for watching and see you next time.